What are the next steps?
So we have to finish the homework assignment on chapter 8, and then we're going to be ready for the next midterm on chapters 5, 6, 7, and 8. So we have to finish the homework assignment on chapter 8. And
So probably like 2 weeks.
Something like this, 2 weeks, maybe, yeah, somewhere there. Okay, that will kind of life. Okay, it is somebody asked work problem from homework assignment number 6 to be solved. So let me start with it, and by that time you have to come up with your questions. Any questions? Even questions that are not directly related with the material that we're discussing now. So people asked me to solve.
Number 6, loop to loop.
Yeah, that one. Yeah, exactly that one. Let's see. So problem number 6. Let's start with this problem from the homework assignment. Oh, okay. I'm projecting something else. Okay. Okay. Yeah, time to start. So in this homework problem, this is problem number 6 from the homework assignment that is due tomorrow or Thursday. So you have loop the loop, and this is the initial speed of the car. So of course we have to assume that this car is moving with very, very low speed. So I don't know how it's going to. Maybe it's a toy car, who knows? Let's say toy car, so it makes sense. Because this is really very low speed, and this means that the radius of the loop is not going to be very large. At least the version that I have with on the screen. Now, we're also going to, we have to assume that the engine of the car is off. So it is practically caustic. Yeah, basically, this think about it as a toy car. And now look what you have. You have chapter 6 is right. This is a chapter 6 homework. Chapter 6 is work and energy. Okay. So this is what you have. You have the loop, and you're looking for the radius of this loop, so that the object that has initial speed p naught right here, which is given, for me that initial speed is 4.3 meters per second. So this is this direction. You want the car to be still in contact with the track when it is upside down. But you're looking for the largest possible radius of the loop. So if you increase the radius of the loop a little bit more, the car is going to fall at this highest point where it is most prone to falling. This means that the car is on the verge of falling from the track, and the condition for being on the verge of losing contact with the track is the normal force to disappear. So you're saying this you must have some speed of the car in this direction, final speed. But the forces that act on the car, the weight and the normal force, F normal, the normal force disappears when you're on the verge of falling. So the only force that is left is the weight. And you want that weight to be a centripetal force in order you to have it to stay on the circle, it to stay on the track. Centripetal force meaning it to be mv squared divided by r. In other words, when you cancel the mass, you want the speed of the truck at the top to be equal to 3 times r, the speed squared to be 3 times r. This is the condition, the car to be on the track. Now let's put together this condition, combine that condition with what they say about the initial speed of the car. So take this, the origin of the coordinate system to be here, so the ground level to be here. You want the energy of the car on this ground level to be equal to the energy of the car when it is up there, moving with speed, with the required speed. No friction, no engines, no external forces. The energy of the car here should be equal to the energy of the car there. The energy of the car, initial energy, is only kinetic energy, 1/2 mv0 squared, because it is at 0 height. The energy of the car when it is at the top is 1/2 mv squared plus some gravitational potential energy, mg, this height, and this height, so mg, the height of 2 times the radius. Yes.
Can I ask a question? When we get lost, just like any problem, we get lost and we are like, where do we go for our next? Like obviously we've got kinetic energy. We need to know our initial and our energy final. But like if we forget where to go next, what's your suggestion? Because I think that's sometimes the hard thing. You're in the middle of a problem, you don't know what to plug in next.
Well,
Is there like, especially for this chapter, is it like just the 3 constants: work, energy,
you know what? The best thing is to have somebody next to you and to you to talk. And this somebody could be a classmate, it could be myself, it could be a tutor, to put you in the right direction, basically. And sometimes just talking with somebody helps to go in the right direction. But again, well, working groups, your classmates are the best resource. And if you happen to be on campus, and if you're in this building, I'm in the office when I'm not in class or in some meeting or something. Okay, so energy is conserved here, no external forces doing work. Yeah.
Sorry, I missed where you got the R.
So R is the height. The height is H is 2 times R. And the gravitational potential energy is mg times the height. And the height in this case is 2R. And now look, the final energy is this expression, but you want, look, in this problem, you cannot even plug in numbers because there is only one number given. So now you want the speed squared to be gr. So here it is, the speed squared to be gr. So this is going to be 1/2 m times gr for the speed squared. And after that you have mg times r. So everything is mgr. But this is 2 times mgr, this is 1/2 mgr. A total is 2.5 times mgr, right? So when you add those mgrs, you get 2.5 times mgr. So 2.5 times mgr. And that's it. So now initial and final energy are equal. So you have 2.5 times mgr has to be equal to 1/2 m times v naught squared. And again, the mass cancels again.
Does that gr need to be squared? That 1/2 mgr squared?
No, I just, the square of the speed is gr.
Oh, okay.
So I didn't take square root because I knew that I was going to need the square. And from here, the only unknown is the radius. Solving for the radius, you get r is equal to v naught squared divided by 2 multiplied by 2.5 multiplied by g. In other words, it's going to be v naught squared divided by 5 times g.
And where's the 2.5 come from?
So this is 0.5 times mgr. This is 2 times mgr. 2 plus 0.5. So 2 plus 0.5. Yeah. Right.
But it's not 2r, isn't it? It's not 2 mg, is it? It's 2r.
Yeah, but multiplication is commutative. So you can 2 times 3 times 5 is the same thing as 5 times 2 times 3 in any order you want. So you can rearrange the order of the factor in a product as you wish. So this is a good problem because it asks you about centripetal force, about total energy. You could have solved it without using the concept of energy, but using energy is much shorter and easier to understand. The energy at any moment of time is the same because there are no losses of energy or input of energy from outside. Okay. Okay, let's see other questions. So any questions from MCAT, from any sources? GRE? Yes.
Can you do number
Number 8 from the homework assignment from chapter 6. Okay. Okay. So you have a bicycle and so I have to define power. So I delete the definition of power, but basically power is defined as work divided by the time during which this work is done. But you know that work of external forces is change of energy. So power is also energy change divided by the time during which this energy change happens. You can say it delta E over delta T if you want. The units are joule per second, and joule per second is called watt. So 1 watt is 1 joule of work done in 1 second. So this is the definition for power. It is well, you can put it in different, so you can demonstrate that power is also under certain conditions can be calculated as force time multiplied by velocity magnitude. But let's see if we need. So here there are the questions about energy. So this person generates 6.5 watts per kilogram of body mass. I guess this is kinetic energy that he generates. So keep in mind that the human body normally consumes and emits as heat about 100 watts, 100 joules per second. Under normal conditions, room temperature and not exercising too much, just as a heat exchange, 100 watt is the power consumption. But here they're giving you the power generated for one body of his mass, which means that the power that he generates. So this is problem number 8, not 7. So the power he generates is given, and well, it is given per unit mass. So the power is going to be a product of his mass times the number that they give, times 6.5. 6.5 to give you the power that is generated in watts by his body. And this power presumably is going to be converted into mechanical work. So the first question, how much work does he do during 120 kilometers? Okay, look. In my definition for power as a product of work multiplied by time, now imagine that work divided by time. Imagine that the work is done by a constant force in the same direction as the displacement. So for that case, the work is this constant force multiplied by the displacement in the same direction. The cosine is equal to 1 because the force and the displacement are in the same direction, divided by t. But displacement divided by time is exactly speed. So you have force multiplied by speed for the power. Alternative way of writing the power, and this is what you need for part A. So for part A, you have the power is given, right? It is his mass multiplied by 6.5. His speed is given. So you have, this is given, this is given. You can immediately determine the force that he is generating during this race. But do you need that? No, you don't actually need this. You can immediately say this. You can immediately say power is work divided by time. In other words, the work is going to be the power multiplied by the time during which he is moving. And the time that he is moving is going to be the distance divided by his speed. Well, the distance, call it d, divided by his speed. This is time. Distance divided by speed is time. Just make sure that you convert the distance into meters, because the speed is in meters per second. So for my version, it is whatever power you have calculated times 120 kilometers is 10 to the third meters divided by 14.5. And you're going to get the number of joules of work that he has done during this race. So directly, you don't need to use speed or any other. Just do this. If you want, you can go through calculation of force, but it's going to give you the same result. So this is part A. And part B in similar manner, let's see what they are. Oh, so now this work has to be converted into calories. Well, so you have to be careful with those units. Calorie is a very misleading unit because you have a big calorie, and one big calorie is 4.186 joules, but you have times 10 to the third. In other words, it's 4,186 joules. And the small calorie, lowercase calorie, which is 4.186 joules, 1,000 times difference. So usually in nutritional labels, by calorie, they mean a big calorie, large calorie, capital C. And they even say that 1 joule is this number of calories, how many calories you have in this number of joules. If you multiply that number by the conversion factor of 2.389, 89 times 10 to the fourth, you're going to get the result in capital C calories. Do this multiplication. So it's interesting to see what are the numbers. If somebody calculates numbers. So let's see.
Do you multiply by 10 to the negative fourth?
Oh, negative fourth, yes, negative fourth, yes. Negative fourth. Let's see what are the numbers that you're going to get. the mass is 70, so you're going to get something like
487.5
for the hour,
for watts. Yep.
487.5.
87.5.
Okay. After that, when you multiply this by 120,000 divided by
4,034,000.
0.10
Yep, 034.
to the 6 joules, okay? 4 million joules. And divided it into, so multiply by 10 to the 4th is going to give you only something like 10-ish calories or something. It's very small power consumption. What do you get when you multiply this 4 million by 10 to the negative 4?
963.84.
Say it again.
963.84.
84 calories. 963 calories. This is probably of the order of the calorie content of one chocolate bar or something. But keep in mind that this is only the energy that he spends for the motion. Simultaneously, his body uses energy for metabolism, respiration, body heat, mental activity. So let's put the numbers here and see if we're going to have that right. 487.5, 487.5, and here is.
No, that one's for the joules. That first one.
Oh, they want joules. Yes, not the watts. They want the joules is 10 to the 6th. So 4.034, 4.034 E6 work, and this is 963, 960.84. Yep, very good job. Okay, any remarks and questions about this? So basically, this problem tells you bicycle riding is not a good way to burn calories. You just burn a single chocolate bar worth of calories. But again, this is only the mechanical work done. In addition to this mechanical work, you have to put all the metabolism that uses energy. And it's probably going to be substantially higher, because 120 kilometers bike ride is really something. This is something like 70 miles. So this is more than the distance to go to Idaho Falls with the bike, and if you try it, you'll see that it's not that easy. Okay. See other questions? So anybody with MCAT, jury problem? So I have some MCAT problems, but I want you guys to bring them rather than myself today. Some of them are not mechanics, some of them are electricity, some of them are. What about GRE type of problems? Algebra, something of that nature? Well, we're only 28 minutes in the session. Yes. From this homework? See what is number 4. Yeah. So number 4, the homework assignment. A slingshot fires a pebble from the top of the building with given speed. The building is this tall, no air resistance. Find the speed with which the pebble strikes the ground. So no matter which direction you fire the pebble, speed is going to be the same. It is just like this example with the fuel tank of the plane that was either going this way or going this way. The speed is always going to be the same. And you'll see that immediately from conservation of energy. So let's say here it is, you fire under certain direction, doesn't matter what direction, with speed v naught, and the pebble is going to go and do this and hit the ground here. So use a coordinate system that has the 0 point. Well, you can use any coordinate system. You can use it 0 point here or 0 point there, the same result. But if you use a coordinate system with 0 point here, since there is no air resistance, the energy at the initial point and the energy at the final point have to be equal to each other. The energy at the initial point is kinetic, 1/2 mv naught squared, plus potential, where h is this height, and they give that height. For me, that height is 30.5. So this is the initial energy. This is the number of joules that this object has in the beginning. At the end, it has to have the same number of joules, but at the end, the energy is only kinetic because you took the height here to be 0. So you're going to have 1/2 mv final squared. And those two energies are equal to each other. Final and initial are equal to each other. So you have 1/2 mv final squared has to be equal to 1/2 mv naught squared plus mgh. And that's it. So you can cancel the mass of the pebble everywhere. It's away. Multiply by 2, take square root, and you get, okay, v squared is equal to v naught squared plus 2gh. The factor of 2 came from this 1/2. And the speed itself is going to be square root of that. V1 squared plus 2gh. Nowhere we used direction of initial velocity. So no matter which way you launch, this way, no matter which way you launch, the final speed is going to be the same.
So when would you take into account horizontal in this situation?
Well, everything is here. So this final velocity contains, so this is final velocity, it contains horizontal component, vertical component. Nobody is asking what are the components. The total velocity is in the energy at the final point. Both components are taken into account automatically. We know that in this projectile motion, the horizontal component never changes. We know that. But then basically this is telling you, here is the pebble. If I do it this way or directly down, it is going to hit the ground with the same speed. This way or this way launching, doesn't matter. Yeah, this is a reasonable, yep.
So work is equal to E final minus E initial, is that right?
This is work of external forces, and there are no external forces here. Gravity is counted as internal.
That's why they're equal to each other.
So no external forces. So the work is change of energy. So work is E final minus E initial. But this is work of external forces. They don't exist. So this is zero. So zero is E final minus E initial. And therefore, E initial is the same as E final. Right? That's
And for any object that's starting above zero, initial kinetic energy will be the 1/2 mv squared plus gravitational potential energy.
yeah, this is what we have, right?
Right, yeah, I was just wondering about for anything that starts above zero. And then
Well, it
zero-
depends when I put my 0 point. Look, I would have said, this is my 0.
And then you don't have to use gravitational potential energy.
So if this is zero height, I'm going to have initial energy is going to be, so let's do, initial energy is going to be only 1/2 mv0 squared. But the final energy is going to be 1/2 mv final squared plus mg h. Right, this is my 0 point, this is my coordinate system. The height now is -30.
What if you weren't at any height at all? Is that?
Well, if I launch directly here, yeah, that will work. The result still is going to be the same. Look, if the height from which I launched was 0, this goes to 0, and you get V final is equal to V initial, something that you know from projectile motion. Whatever speed you launched, this is the speed that is going to hit the ground if it is horizontal. But so again, the choice of 0 height is up to you. You just have to, once chosen, you have to be consistent. You have to always use that. Okay, let's see other questions. Maybe something not homework only related. This homework is relatively short. So next homework is also not very long. The practice test. Oh, did I post the practice test?
Yeah.
So start looking at the practice
do-
test.
Yeah, can we do number 16 off the practice test?
When is our test?
So it's not scheduled yet, but it's roughly in about 2 weeks or so. So maybe not next week, but the week after that. We'll see how. We have to finish chapter 8, and tomorrow we are starting chapter 7, so we're getting close. See where's the practice test. Okay. So the practice test, which problem?
16?
I managed to get all the way to problem 16. Wow. Oh, this is the ballistic pendulum. This is what usually you get in the lab. But you know, we haven't done chapter 7 yet. So this problem is from chapter 7. Did you do the lab already?
No, I don't have lab.
Usually lab is required for people that are biomedical majors. So
I've got it.
So let's solve this problem after I talk about linear momentum in class. And it is a good problem because in the lab you do the experiment actually, not with a bullet, I hope, but you do the experiment with something, some ball, I guess, or some other projectile. And it is a good problem to go over, but let's do it in class. If you remind me after, so probably tomorrow I may be able to talk about linear momentum and conservation of linear momentum, and then this problem together with conservation of energy is going to be a good example. What about, so we did something like problem 13, right? Because we had this roller coaster, but it was different formation, but pretty much the same idea. We did problem 15 as a homework problem in class. Let's do problem number 14 from this practice test. Problem number 14. So you have horizontal surface, no friction, and 300 Newton force. It's just, so here it is. Crate or whatever object it is, a horizontal force of 300 Newtons. So here is this horizontal force F equal 300 Newtons. And you go from this point all the way to this point right here. Yes. So this displacement is also given. Call that displacement is 20 meters. It's just a problem to, what is the final speed of the crate? The mass of the crate is given. How would you handle this? So initial speed of the crate is 0. What else is given? Displacement is 20 meters. You need one more number. And that additional number is acceleration. Is force and force divided by the mass, Newton's second law. So you have your three numbers now. Force is 300. The other forces cancel out, right? You have normal and gravity cancel out. So the net force is 300 Newtons. The mass is 50. 300 divided by 50 is 6. Acceleration is 6 meters per second squared. So here are your three numbers. You can answer what is the final speed V using the formula which connects those variables, a formula that doesn't contain time. That is, V squared is equal to V naught squared plus 2 times acceleration times displacement. So this formula directly is going to give you the final speed. V naught is 0. A is 6, we said. Displacement is 20. So you have 12 times 20 is
240.
yeah, 140. 240, right? this is part A. Part B, how much work is done? Well, the two other forces don't do any work because they're in direction perpendicular to displacement, and cosine of 90 degrees is going to be zero. So the work of the other two forces is zero. The work done by the force F is just a product of the magnitude of the force times magnitude of displacement. The angle between them is zero, cosine of zero is one. So cosine of 0 degree is one. So it is just a product of the force times displacement, 300 times 20. And this is going to give the work in joules, 6,000 joules. And part C, coefficient of friction now to keep the crate moving at a constant speed. So now you have friction and you have some kinetic friction because you're still moving, but now at a constant speed. So look, so this is part A, part B. Constant speed, part C. Constant speed V, constant, for one-dimensional case, means acceleration 0. Acceleration 0 means net force 0. Well, we already have that normal and gravity force cancel out. So net force 0 means friction is equal to this pulling force of 300. This is what it means, 0. Equal in magnitude, they are in opposite directions. Well, but you know that the kinetic friction is coefficient of friction times normal. In this case, the normal force is just the weight mg. So now the condition for constant speed means this friction force to be equal to your pulling force F. In other words, looking at this part of the expression, you have coefficient of friction should be the pulling force divided by mg. And it should be the, So this is the answer for part C. Great. So look, this problem 14 contains all new material that you're familiar. Yes.
Where did you get the 0 degrees?
They say horizontal force, right? Horizontal force, horizontal displacement. So here's the force, here's the displacement. The angle between them is 0.
When would you use the 180 degrees?
Well, if the displacement is still this way, but the force is in opposite direction, the angle between them would be 180.
That's when like friction is your only work.
Yeah, in this case, the work done by the friction is going to come with a cosine of 180. So cosine of 180 is going to be -1. But they are asking, in part B, they are asking the work done with no friction, only the force that the work done by the pulling force that was there. Other. Okay. So we're not ready for problem 12. We're not ready for problem 11. We can fancy an answer problem template. This. Not ready for problem 9. Problem 8, we can answer. So the rings of Saturn are pieces of ice and dust and rocks. And they say that one of those ice cubes on Saturn's rings is circular ring, of course, with radius of this number of kilometers. And they want you to figure out the speed of this piece of ice. This is problem number 8 from the practice test. So here is the Saturn, and here is the orbit of your ice cube. So they say that this radius of this orbit is given. That radius is
100,000 kilometers.
yeah, so this is 10 to the 8th. No, 10 to the 8th, yes, 10 to the 8th meters, right? 10 to the 8th meters.
The eighth or seventh?
I think 10 to the 8th. Right, this is 10 to the 5th times 10 to the 3 is 10 to the 8 meters. I think, yeah, you do the arithmetic, but I think that should be it. They're asking to find the speed of this ice cube. Is what? Notice that this velocity is tangential to the circle, right? So now what? Necessary and sufficient condition for circular orbit is the force, which is only gravitational force, should be centripetal force, mv squared divided by the radius. But the force is gravitational, and therefore it is given by Newton's law of gravitation. So it is gravitational constant times the mass of Saturn times the mass of the ice cube divided by the radius, the distance between them squared, like this. In other words, your equation looks like this: gravitational constant, mass of Saturn, mass of ice cube divided by the distance between the center of Saturn and the ice cube should be equal to mv squared divided by r. And you see that the mass of the ice cube cancels out. 1 power of the radius of the orbit cancels out. And you get that the speed squared is equal to gravitational constant times the mass of Saturn divided by the radius that is given. And the speed itself is square root of this expression. So you have to take the gravitational constant from the front page. The mass of Saturn is given, and the radius of the orbit is 10 to the 8 meters. And it's going to give you the speed after you take square root of this expression. We end it here, or should we? Let's see if there are questions from your side. If there are no other questions, I'll end the session here, and we're going to again, if next Tuesday I don't have some meeting or some class, we're going to meet again if you.
You said we can't do 9 or 12, right?
Uh,
Learn Chapter 7 yet?
No, those problems are from material that we haven't covered yet, chapter 7 and 8.
Okay.
So we just have to. But I want people also to try some of those questions independently before they see how to do it. And again, if you're preparing for MCAT, bring physics problems, bring math problems, GRE, dental, optometry exam. We're going to do actually the human eye the second semester in some detail. Of course, not the details that are required for optometry, but still you can design and you can produce your own eyeglasses if you want, which is not such a big deal. Okay, so see you tomorrow in class. So if there is a conflict, once we schedule the midterm, we can talk.
Okay, okay, sounds good.
Where are you going to go?
Cabo, Mexico.
Mexico?
Yeah, my mom takes us on trips. So
Wow,
yeah, should be a lot of fun.
that's